So our first example of using the idea of work. Okay. Let's imagine that we've got something that's 2 kilograms, and what I want to do is I want to lift it a height here of 4.25 meters. So how much work does it take to lift this? Well, free body assuming we're going at constant speed, I want to lift it. So if we're going at constant speed, I'm going to explain why constant speed is going to be important for the next example. But if we're going at constant speed, I want to lift it. So that means that we got mg down. This force upwards has to equal mg. Now work is going to be mg, so if that's the distance I lifted, then force times distance is work, so mgh. And so that would be equal to 2 kilograms times 9.81 times 4.25, and so that comes out to be 83.4 joules. So that's the energy that it took to lift something. Again, a simple almost one-step calculation right here. So don't get fooled and think energy is very complicated. Now, let's also consider another example. Let's have an inclined plane. Let's say it's inclined 21 degrees. We have a mass here. It's still 2 kilograms. To make this easy, we're going to assume this is a frictionless inclined plane. So it's covered in ice or something, so it's got like virtually no friction to it. And let's say that the length of the inclined plane is going to be 11.9 meters. Okay. Well, if you do a little mathematics here, that tells you the end of it. The height here is going to be L sine theta. So the height is 4.25 meters. So the height is going to be exactly the same as it was before. So before we had a block and we lifted it 4.25 meters. Now we're just going to exert a force pulling it up the incline and see how much work that we do. Well, we look at it, free body diagram. Whenever you have forces, do a free body diagram. We got mg down. We got the normal perpendicular to the surface. We have our applied force. Now, if we're going at constant speed, again, if we're not going constant speed, that makes the problem more complicated. But if we're going at constant speed, then that means that the perpendicular component of the weight has to balance the normal, and the parallel component of the weight, the parallel component there is mg sine theta, and that has to balance F. Okay, so that means that we can now say work equals F times X. So the work is going to be mg sine theta times the length L. So the work is going to be 2 kilograms times 9.81 meter per second squared sine 21 degrees times 11.9 meters. And so that comes out to be 83.7 joules. Okay, now that is actually the same number. Remember before we had 83.4 joules. This is our least significant digit right here. I guess that should have been 2.00 kilograms. But that's our least significant digit right there. So that means a small change there means that these two numbers are actually the same within rounding error. And so that means that if we have an object and we lift it some height h, or if we have the object and we go up an inclined plane and it's still the height h, okay, then the work on the left is equal to the work on the right. Okay, so the work is the same. The work is still going to be whatever it is. And so so the work is still the same. The work on the left is mg h. Well, on the right we have L, so the work is the force Okay, so the force is mg sine theta times L, but L sine theta is H. So work equals mgh, just like it was over on the other side there. So they're both mgh. So you end up doing the exact same work, just picking something up or sliding up an incline. So why would you slide up an incline if you do the same work? Well, because the force was mg sine theta, whereas the force over here, force on the left, was mg. Well, sine theta is always less than or equal to 1, so the force on an inclined plane is going to be less than the force you just picking it up. So that means a smaller force ends up doing the same work. And again, we ran into this sort of issue when we talked about pulleys. This is a mechanical advantage. You got the same amount of work doing, lifting something, but you did it with less force. Again, with a pulley. Remember, if we had a pulley and we had a rope like that, and we had some mass m, okay, compare that to just, you have some mass m, the tension is mg. So if I lift this some distance h, then the work is going to be mgh. Whereas here, if I have tension, then the tension is going to be, the tension is going to be 1/2 of mg, because you got two tensions pulling up. Remember, we had two tensions pulling up, and that balances the mg down. So two tensions equals mg. So now, if I want this to go up some distance h, I have to pull this 2h, because I got to make both sides go up by h. So in order for the mass to go up a distance h, I got to pull 2h. So that means the work is going to be the tension 1/2 mg times 2h. So the work is mgh. Okay, so that means that I lifted it the same distance h, but I did it with half of the force. But I had to go twice the distance to have the same amount of work done, to lift it by the same amount. And so, again, this is the idea of a mechanical advantage. It's what these simple machines do for you. They allow you to use a smaller force to do the job of a bigger force. But you don't get something for nothing, because the smaller force you have to go farther distance with. So you still have the same amount of work done. But it makes it easier because you have a smaller force.